Good afternoon, everyone, and thank you for joining us in this series of presentations that we've been putting on. Hopefully, you've been finding them educational and answering some of your questions. Today I was asked to give a presentation on improving evaporator efficiency. And when I first sat down to start working through this presentation, I thought, oh, this is going to be easy. It's actually pretty simple. And the solution there is simple. Buy a new energy-efficient Caloris evaporator system. Done. However, as I thought, okay, I think you're probably going to be looking for a little more from us on that. So I then sat down to figure out, okay, how do we define evaporator efficiency? And usually it starts with energy efficiency. How many pounds of water can we remove for a pound of steam, or how much electrical power are we consuming for evaporating a pound of water? But in a lot of the projects we've worked on, it's not just energy efficiency we're focused on, it's production efficiency. You've got daily production capacity that you're trying to achieve, and how much energy are we consuming to achieve those pounds of product discharge. Also, maintaining consistent discharge concentration from the evaporator system, because usually there is a downstream processing system, and while we can do everything we can on the evaporator, if it's discharging at lower solids and it's going to a spray dryer, that spray dryer is going to consume more energy to get rid of that extra water. Also, product losses. So, production efficiency is also a factor. And then operational efficiency. How many hours a day are we remaining online versus CIP time or downtime for cleaning? And what are your chemical consumption costs and your losses? So as we look at those, that multiple ways as to how to, what defines truly an efficient evaporator process. So starting on energy efficiency, there we go. When we're working on evaporators, energy efficiency is basically this simple equation here. Heat transfer, how much water are we trying to evaporate is how many BTUs or kilocalories of energy do we need to put into that system to remove that water. And that is a function of the heat transfer coefficient, which is product specific, the available surface area, and the temperature difference across the heat exchange surface. So it's those three variables: the heat transfer coefficient, surface area, delta T. Now the U coefficient is product specific. There's not a lot we can do to improve it. Some products, we get a better heat transfer coefficient when we boil at a higher temperature, or if we can improve the turbulence of flow across the heat transfer surface. But usually a lot we can do there. It is a dynamic value. It decreases as we increase concentration as we go through an evaporator. So every pass through the evaporator, we're having a lower U coefficient, and it's harder to overcome that and to continue to remove water. Fouling in the evaporators is always a dynamic factor that we are trying to overcome to maintain consistent production, and the presence of inert gases. Now, delta T is the solution that most of you who operate evaporators deal with on a daily basis. You start with a clean evaporator, you start evaporating, and in order to maintain capacity and maintain evaporation rate, the tool that you have available to you is increasing the delta T. Now, that's actually consuming more energy, so it's less efficient than it was at the beginning of the run. And the higher the delta T, the faster it fouls. And usually what you're dealing with increasing delta T is overcoming fouling in order to continue for a full run of the day. And it's also limited by the compressor device capabilities. Whether you're an MVR turbofan and you're increasing delta T by increasing the fan speed, or you're a steam heated with a TVR and you're increasing your delta T by putting more steam to the TVR. Steam pressure, fluctuations in steam pressure are always a challenge for maintaining steady evaporator performance. cooling water temperature and supply. And then, there's the product limitations, heat sensitivity, viscosity, boiling point elevation, which all limit what we can do with delta T. And then there's surface area. Always the nice solution to improve an evaporator performance is, let's put some more surface area into the system. And that usually means putting in, an extra calandria, replacing a calandria. That's a higher capital cost and is usually only justified when you're also looking for increasing and achieving higher production capacities. Energy efficiency. So we're looking at steam heated evaporators and MVR, mechanical vapor recompression evaporators. So a steam heated evaporator, 1 pound of water in a 1 effect evaporator, 1 pound of steam going into the shell will evaporate a pound of water. A 1-to-1 pounds of evaporation per pound of steam consumed. A 3 effect evaporator, direct steam heated to the first effect, you're going to evaporate about 3 pounds of water per pound of steam. More efficient use of that steam, higher energy efficiency. Then we go to TVR. Now I've got the picture here on the lower right. That's a 3 effect evaporator with TVR compression across the first 2 effects. And we are effectively getting 5 pounds of water evaporated per pound of steam. You've got 2 pounds of heating vapors going into the first effect, evaporating 2 pounds of water, which heat the second effect and evaporate 2 pounds of water. So we've got 4 pounds of water evaporated so far. That TVR draws 1 pound of the 2 pounds being evaporated. You're left with 1 pound of vapor going to the third effect to evaporate another pound of water. You boost the vapors you drew into that TVR with a pound of steam. There's your 2 pounds of vapor going to the first effect. 5-to-1. Energy efficiency is what it's commonly referred to. It's not that exact because you have venting losses and the TVR has to be operating in its ideal performance range. So it's never quite 5-to-1 as we might theoretically design it on paper. Electrically driven MVR evaporators, now we're talking horsepower, or kW of power consumed. And it's very common, and they're usually 1 effect systems. And very commonly for most of our product applications, we're looking at 100 pounds of evaporation or up to 130 pounds of evaporation per horsepower of input to the turbofan. But, you look at this, we're comparing apples to oranges. And, how do you compare energy efficiency of these 2 different types of evaporators? And that really depends on your energy costs. So energy efficiency is a function of energy costs. And for this example here, we have a typical MVR or a typical pre-evaporator pre-concentrating skim milk to 36% solids condensed. So 100,000 pounds an hour skim, 4x concentration factor, we're evaporating 75,000 pounds an hour of water. We operate that 8,000 hours a year. So we've got an MVR evaporator with a 670 horse turbofan motor, drawing about 475 kW average consumption. If we're about 7 cents kilowatt hour for our energy cost for over that 8,000 hours, it's $266,000 a year in energy consumed to achieve the water evaporation. Comparison to a TVR evaporator. Let's say we've got a 4-effect TVR compression over 3 effects. So theoretically, we've got a 7-to-1 steam economy on this. And so we're going to consume about 10,700 pounds an hour of steam. At 5 cents per 1,000 pounds of steam energy costs, 8,000 hours, you're looking at $428,000 a year for steam costs. So on paper, if I'm designing a new evaporator at these energy costs, even though the MVR evaporator may initially cost more, let's say $600,000 more in upfront capital, the ROI, the payback on that is less than 4 years, and then it's money in the bank every year after that. So it's very likely I'm going to propose an MVR evaporator for that scenario. But what if your energy cost is 12 cents a kilowatt? Say you're in California. Well, that MVR is actually $456,000 a year to operate for that 475 kW. And Economically, the steam heated evaporator suddenly makes more sense, unless there are extraneous circumstances like you need to buy a steam boiler. Now you've got costs there, or you have to permit a steam boiler. So there's always a cost-benefit analysis associated with achieving what is the most energy efficient evaporator. So that's what I wanted to cover generally in energy efficiency. Then as I sat down to think about the other factors, production capacity, operational capacity, I came up with a list of opportunities to improve efficiency of an existing evaporator. Because often our customers have existing evaporators, and the first thing they want to do is they want to improve the efficiency of that evaporator. And came up with 11 bullet points here, and it didn't even begin to touch into the areas of restreaming the evaporator flow paths and retubing an old calandria where you've got some plug tubes to get the heat transfer area back, or maybe even adding extra surface area, all things we've done. But these 11 things here each of these we have implemented at Caloris over the last 15 years, 14 years, at somebody's evaporator to achieve an efficiency improvement. Vacuum leaks, of course, and optimizing venting. And that's always the first thing we need to look at and the last thing we need to check on any evaporator. Proper feed preheating and regenerative preheating, utilizing available BTUs of energy that might otherwise be going to waste. Improving the liquid distribution in the tube wetting on the existing evaporator to more efficiently utilize the available surface area. More efficient or maybe even more frequent CIP cycles. And in fact, and I'll get into a few more slides here. If fouling is causing you to consume more energy, there's a certain point of trade-off where you're better off stopping, cleaning, and getting back online and being more energy efficient, rather than pushing the evaporator, for an extended number of hours and just shoving more energy into it to keep it running. Maintaining saturated heating vapors, operating, optimizing, modifying possibly the compression devices, be it the turbofan or TVRs, the waste heat systems, condensers and cooling towers, general routine maintenance, feed preconcentration, and automation. All actions and steps that we've utilized to improve the efficiency of somebody's evaporator over the years. Vacuum leaks and venting. It's every presentation I think I've ever done on evaporation and probably ever will do, this slide is pretty much at the front of it. And this is, these are quotes that we've used. 90% of all evaporator problems are due to vacuum leaks. Anybody who owns an evaporator that operates under vacuum knows that. And there's no such thing as a small vacuum leak. And vacuum leaks introduce non-condensable gases into your system. And an evaporator that's operating under a partial vacuum condition, you want to utilize that available surface area. And as I display here in this, and I don't know if you can see my cursor, but here on the lower end of the calandria, this is trying to depict that we've gotten some non-condensable gases into this evaporator shell, and those gases are displacing steam from getting to the surface area. And I'm losing area. And in my equation at the beginning, that A is getting smaller, and the only thing I can do is put more delta T in there to keep evaporating, which is just less energy efficient. So what do? We go in, first we find all of the leaks. Once the leaks are done, then the next thing is venting. We need to get those non-condensable gases out of our heat exchangers. Typically, calandrias, preheaters are vented at the top and bottom so that we get a good draft of those non-condensable gases out of the shell, keep them from collecting. And we always do it at startup, and occasionally we've got to go back and rebalance and modify, replace the restricting devices on those vent lines. Typically, we're using orifices. So sometimes you'll see valves, but we prefer orifices because it's harder for somebody to change it. And once you balance a calandria, and a heat exchanger on its venting profile to what you believe is its optimum condition. If you do that with an orifice, it's a little more challenging for somebody to change it. But you do need to document what orifice size works best. Make sure that that is well documented and available for reference, because periodically those lines do get opened, and somebody's got to know what size orifice to put back in there to get it back to design and optimum conditions. And it is important to periodically check those. Now, sometimes somebody has a calandria they don't think is venting properly, and if you take the orifice out, it'll vent really well. But excessive venting leads to energy loss because you're sucking useful vapors out of the system unnecessarily. That is inefficient. And we do, and you'll see this on an upcoming slide, utilize venting in order to vent through preheaters to actually minimize waste losses by having generous venting on a calandria and yet reducing and minimizing the venting losses going to the waste heat system. So that's venting. First bullet point I had on my list of items. Preheating and insufficient preheating can be a killer in an evaporator. And we have faced this multiple times, especially when somebody takes a used evaporator, tries to repurpose it in a new location for a different purpose, and they neglect the preheating step. And what you visualize here is you have your product coming in the top of the heat exchanger, flowing down that heat exchanger tube. But if that product is not at boiling temperature, when you start putting heat to the outside of that tube shell and putting heat into your product, your calandria is now a preheater, not an evaporator. And you are not effectively utilizing that surface area of the calandria for evaporation. Your A effectively is getting smaller. And this becomes particularly troublesome in a multiple effect steam heated evaporator, because if you're preheating product as it goes into the first effect and not fully utilizing it for evaporation, you are not getting those vapors into the second effect, and you're not getting full effect function out of the second effect or any subsequent effect where that lack of vapors is unavailable, to drive evaporation. So this is a description here of utilizing, vapor liquid, typically shell and tube preheaters. And how do we optimize those? So we have we have feed coming in, and that's the middle one, preheater 11, and that's drawing vapors typically off the main calandria. And this is where we get to the point of utilizing, vent vapors as our heating source to a preheater. So that line coming into preheater 11 is actually the vent line coming off the top of the main calandria. And now we're preheating some feed with vapors, heating vapors from the main calandria shell. Now we need to heat further. Let's say that we're, going to a pasteurization step. So now we have a TVR that pulls vent line, basically the vent line from the bottom of that main calandria. Steam boosts those to a higher temperature. Now we've got our heating source, a higher temperature heating source for achieving pasteurization temperature in preheater 12. And we've got venting top and bottom of that main calandria. And then the preheater 13 is interstage. And that's important in a lot of applications where we've got multiple pass product through a single calandria. Each time we get back to the top of that calandria, we want to be at boiling temperature. Again, if we're not at boiling temperature, we've got some preheating as it enters those calandria tubes, not effectively using that surface area. Not shown here is also the option of having a shell and tube preheater where the vapors are coming off the last effect before they go to a surface condenser. And we're effectively using waste heat that would otherwise end up in the cooling tower as a feed preheating source. And you ask, why don't we do that on all evaporators? Well, there can be a trade-off between regenerative heating versus the vapor condensate coming off the evaporator. And it's typically either or. preheating versus condensate or waste heat condenser, because we're dealing with the relatively same heat source temperature. And so it's difficult to extract that energy twice. Regenerative preheating. Now, this is a case where, we've typically got hot vapor condensate coming off an evaporator. And if you're just sending that to drain, that's BTUs going down the drain. And even for some plants where they are discharging directly outside the plant, you have a temperature limit on what you can discharge at. And if your evaporator is running hot through the day and your condensate cal water temperature gets higher, it can actually be a problem for you. So this is a configuration here where we have a cold, pasteurized feed coming in, and we don't want to pass that directly against the hot vapor condensate because it's a pasteurized product side. We set up a recirculated loop of potable water that goes through the plate heat exchanger counter to the cold feed coming in, and we heat right up to our preheat temperature through that one plate heat exchanger. We then run, the recirculating potable water as it exits that plate heat exchanger is now going to be cold. And so we heat the recirculated potable water against the cal water in a separate heat exchanger stage. So we extract those BTUs. Now we have cool vapor condensate discharging. And we've got a little steam heating loop on that potable water loop to boost the temperature as we may need to achieve our desired preheat temperature. So it's a trade-off. Does your application, do you want hot vapor condensate available, in which case we're going to utilize waste heat vapors coming off the evaporator for preheating, or do you desire cooler vapor condensate, in which case we're going to utilize regenerative preheating in this manner? So first three bullet points, as I went through my initial list there. The next one was liquid distribution. And we've done a number of rebuilds on evaporator systems modifying the liquid distribution. And this is critical to good functioning performance of any evaporator system. They have good wetting of all of your heat exchanger tubes, particularly if it's a falling film evaporator, as is shown here. So we've got our feed coming in the top, and we've preheated it to above boiling temperature, because a little bit of extra energy is not bad. We want to make sure we are at boiling temperature when we get into the tubes. So we've got to restrict it a little bit as it comes in to prevent flash in the pipeline before it gets into the calandria lid. And now the first thing we want to do is distribute that against the lid of the calandria to dissipate and allow that flash to take place. So now the liquid, as it gets into the pan and onto the distribution plate, is at boiling temperature. And we've got a little flash energy, flash vapor in this chamber here. So we've got to have some chimneys or some place for that vapor to get out. We also have to make sure that we've properly designed that distributor plate to maintain a uniform liquid level at all times. If your liquid level isn't deep enough, then you're going to have sections of the plate that are going to run shallow and are starved for product. So a lot of engineering that goes into proper design of a distribution plate here. And that's not even to mention making sure those holes line up properly. They've got to be matched properly to distribute liquid all around to all of those tubes. So it falls on the meat of the tube sheet plate. You certainly don't want that liquid falling down the center of a tube, because there's no heat transfer taking place then. It's just free fall of liquid through a tube. There are variations of distribution, of course. Spray balls are used for that initial distribution of liquid and allowing it to degas and flash a little excess energy off to boiling temperature before you then distribute through a plate. We've rebuilt some evaporators where that distribution plate is not there. It's just a spray ball spraying product down onto the tubes. And in general, it works, but it's an inaccurate method, as far as we're concerned, on distributing the liquid evenly and uniformly to all the tubes. And we have rebuilt a number of evaporators out there, taking out the spray ball distributor and putting in a distribution plate of some kind with a pre-distribution plate, like we showed in the previous, so that you get a uniform liquid level on your distributor plate so you can get the product distributed to all of the tubes properly. Why is that important? Tube wetting. If you have a tube that's running dry, if you've got poor, uneven, disrupted liquid distribution to all of your tubes on your calandria, inevitably it's going to lead to your tube's going to run dry. You're going to get some burn-on or precipitation of product solids on the inside of that tube, which is an insulating layer. And right away, you are killing that U coefficient part of the equation. It's it's a resistance to heat transfer. And if it goes long enough, you're actually going to plug that tube, and now that's a tube that's no longer in service at all for evaporation. One thing, in addition to modifying the liquid distributor to uniformly wet the tubes, say you've got an evaporator that's got some years on it and has been repurposed, or its operating conditions have changed. We find that maybe for certain products, we can add product recirculation from the lower sump back to the top so that we effectively get a higher volumetric flow of product within each pass of the evaporator so that we can get that wetting rate up, reduce fouling, reduce the rate of fouling, your heat transfer efficiency, the U coefficient remains where you want it to be for more of the day. Better performance. So if you're operating an evaporator and your tube starts fouling, as I mentioned before, you have one solution, delta T. Where you increase the delta T to overcome the resistance that you're facing in order to maintain your evaporation rate. But of course, that comes at the cost of energy. And very likely you're increasing your rate of fouling. So that now leads to cleaning. If you have an evaporator and you don't clean all of the deposits off those heat transfer tubes, you start the day with a lower U coefficient. And for the rest of the day, you are already behind on what you could be. What are some common CIP cleaning issues? Insufficient chemical strength. If you don't have proper chemical strength or temperature, you're just not getting all those deposits off the heat transfer surface. Or insufficient time. Somebody's been tweaking the CIP cycle times in order to maximize production time. At a certain point, you're not getting a thorough cleaning. Or running too long between cleaning cycles. And it's, of course, you're under production pressures and you need to push product through that evaporator. But at a certain point, the longer you run, the more you foul, the longer it's going to take to CIP. And if you don't CIP it properly, you begin the next run behind the 8 ball and you just never catch up. So for some products, such as permeates, where you've got some minerals that have a tendency to precipitate out and foul the heat transfer tubes, it makes sense to go with an intermediate rinse to get those minerals off. And you can, if it's minerals, you can get away with just an acid rinse that then can be more quickly flushed out of the system than a caustic can. And you run, say, 10 hours and you've started to foul out, rather than push another 10 hours with fouling and all you can use is delta T, to hammer it home for the rest of the day. If you stop and do a good cleaning, you start with a clean evaporator for the second part of the day, you are much more energy efficient for the remainder of that day. And when you look at production efficiency, it's all about maintaining consistent discharge solids from the evaporator system. And because that impacts you downstream, be it a crystallizer or be it a spray dryer, you're going straight to the spray dryer, you've got to evaporate more water because your solids dropped for the second half of the day. You're burning energy in the dryer. block spray balls, insufficient spray patterns, in the distribution pan, as we talked about before. You know, is it misaligned or is it not level? We've seen both of these in evaporators over the years. And in either of those cases, you are not properly distributing and keeping your tubes wetted. And on the lack of distribution spray pans, if you're not properly spraying a pan, you can actually have a distribution holes block off from the bottom side. If you look down from the top, you might not even notice. The CIP spray is not being directed at the proper problems. Now that's usually more in the lower sumps area, not directly impacting heat transfer area. Mixing the spray balls up. You know, if somebody takes them out and puts them back in the wrong place, you're no longer effective at cleaning. And again, liquid level. And we've seen this in some evaporators where they go to CIP and they're evaporating so much water in the first stages of the evaporator system that it's running dry on the back end, high chemical strength, but just not enough liquid to distribute to all of the tubes. And I know I'm running a little longer than 30 minutes here, so I'll try and step it up a little bit. Superheat. You know, so you've got a steam source that you're using for heating your heat exchanger tubes. If that steam vapor source is superheated, when that vapor contacts the outside of the tube, the only thing you're transferring is sensible heat until the vapor temperature cools to saturation, where it can begin to condense, and you get that release of latent heat, 1,000 BTUs of energy released for each pound of steam condensed. And it seems like a simple thing, but in so many places we've seen it overlooked. And you've got superheated vapors going in and just not effectively utilizing that available heat transfer area. You know, and it's as simple in some cases as sticking a nozzle spray into the vapor inlet. And all you're doing is saturating, dropping the temperature slightly of that superheated vapor to saturation. Now when it gets to your heat transfer surface, you're going to immediately start condensing and maximize the heat transfer efficiency on that surface area because you're taking advantage of latent heat transfer. In a turbofan takes a vapor, compresses it to a higher pressure. Therefore, automatically, it is a superheated vapor when it comes out. And so we actually de-superheat spray into the suction of the turbofan because it also has the added benefit of washing off potential deposits, that may be carried over with the vapor. And turbofans are very forgiving for this. And what we end up with is a saturated vapor coming out the discharge of that turbofan and a little bit of water spray that's helping to keep that fan wheel clean of deposits, and which helps keep it in balance, lowers your vibration issues. While we're on turbofans, it's a vapor pump. So you've got an old evaporator. Other than maintaining it, which is very important, what can be done to improve efficiency? And you're taking a vapor in, you're compressing it with a wheel, with a fan blade basically to a higher pressure. Well, there's one thing that's been done, is replacing the impeller wheel. If you have a turbofan that's 20 years old, very likely it's probably a stainless steel impeller. In today, turbofans, we're getting an extra 2 degrees or more compression ratio off of the same size impeller because of different materials of construction, super duplex stainless that allows for a higher wheel speed, and they've also done some very good, dynamic modeling on these impellers and modified their shapes and designs to even get a little more compression out of the same wheel speed. And we've done projects where we replace the existing wheel of an existing fan and can get another 2 degrees compression out of that. We may have to replace the motor. But that's an existing, most of the capital equipment is still being utilized, and we're getting some more delta T out of that equation. A comment on turbofan safety. This is a spinning, I want to say high-speed device. It's 3,600 RPM typically, sometimes lower as the wheel size gets bigger. You never want to overspeed a turbofan beyond its design criteria. And it all comes down to the materials and mechanical strength of that impeller wheel. If you overspeed it and you do it for too long and you get mechanical stress failure of that impeller, it can come apart and create shrapnel, and it's not a situation that anybody wants to deal with. And you never want to mess around with defeating the vibration monitoring of that turbofan. It's telling you information about vibration for a purpose. You need to deal with something if it's telling you it's got vibration issues. Don't disable it to keep running. And always keep an eye on the lubrication system. TVRs. So we've got steam motive compression, for that TVR efficiency. And old TVRs, that motive steam nozzle does need to be routinely inspected. And you've got to pull it out. You've got to look at it. And it's a highly engineered device there where you're putting motive steam in and drawing suction of vapors out, compressing them to a higher temperature, higher pressure as your heating source. Remember that model of my 5-to-1 steam efficiency with a compression across effects 1 and 2 of a 3-effect evaporator. Over time, steam will erode away the shape of that motive nozzle, and it periodically does need to be replaced. All depends on the quality of your steam. There are nozzles out there that have been running 20, 30 years and still look fine. Others have been running 5 years and are ready to be replaced. And it all comes down to energy efficiency on the performance of this TVR. These TVRs are engineered for a very specific compression ratio, a certain volumetric flow of vapor being sucked in relative to the steam being used. And if that suction vapor gets starved in any way, or you try to push more steam into the motive nozzle for a higher delta T, you're getting beyond the design parameters of that original TVR. And at a certain point, it just becomes a steam heated device, and it's no longer sucking vapors or compressing anything. And at a certain point, that 5-to-1 efficiency of that 3-effect evaporator suddenly becomes a 3-to-1 efficiency, either because that motive nozzle is eroded and not functioning properly, or you're just trying to push so much steam into it. So optimizing TVR performance. Routinely check that nozzle. Regulate the steam pressure supply to the control valve. Now, they are designed to have a certain range of control where you can increase the steam supply to the nozzle, overcome, tube fouling, getting a little higher delta T. There is a range that they will work in efficiently without significantly impacting your overall system energy efficiency. But it's not a very broad range. And for example, if you have an evaporator and you've changed the product application for it, over the years, it may be time to actually replace the entire TVR to get back to an operating condition that is truly energy efficient. Waste heat systems. It's if you've got mineral scaling in the heat exchanger of your surface condenser, or you've got poor venting and you've got non-condensable gases that are collecting in there, you're not efficiently using the available surface area of that condenser. And the effect is that you can't condense all the waste heat coming off that evaporator. And the back end of your evaporator temperature starts to rise. And the only way to maintain evaporation is to increase the front end temperature. Your whole profile increases, fouling rates go up, nothing is in your favor, and you're just consuming more energy. Periodically check and potentially clean the mineral scale out of your surface condenser. And then, of course, the cooling tower. If you've got fouled or damaged packing, you're just recirculating hot water and not giving it an opportunity to do its job as designed. General maintenance, and I'll try and step it up here, pump seals, routinely monitor and check pump seals and maintain good seal water pressure. Gaskets, routinely check and change your gaskets. It's all about minimizing and preventing vacuum leaks and maintaining good product flows, good tube wetting, all of the things I've previously been discussing. Instrumentation, make sure it's functional and calibrated. You're making decisions about operation of an evaporator usually off the instrumentation, and if you've got bad data, you're going to make bad decisions. And again, vacuum leaks. Preconcentration of the evaporator feed is a very effective way to improve the energy efficiency of the overall concentration process. In many product applications, it's more energy efficient to remove the initial amount of water using, say, an RO membrane system, like we're picturing here. It's pump energy versus steam energy, and very efficient to find the optimum combination of pre-concentration before you go to an evaporator. Now, you do need to be careful simply bolting an RO pre-concentrator onto the front of an existing evaporator system, because that totally disrupts the U coefficients and the evaporation duty and potentially the wetting rates. All the different factors of that evaporator have got to be reevaluated before you just simply implement RO pre-concentration. So it's got to be properly engineered and integrated. It's never just a simple, just remove some water on the front end. My evaporator should be happy. No, it may get very unhappy unless it's done properly. And controls and instrumentation. And a controls person will tell you there's never any such thing as too much controls, but there's a lot that can be done for good decision making when you've got data about the mass flow and the total solids, the density at different points within your evaporator system, the volumetric flows on the front end, or even on vapor flows occasionally. Conductivity and turbidity typically on the condensate streams, but also we are using it on the product streams as well, in particular for optimizing CIP cycles. When you start pushing flush water into the front end of an evaporator, it takes time to push the solids out of the system. And you want to be monitoring how you're doing and how quickly that's falling off. You can optimize the duration of that flush and all of your other subsequent CIP cycles, reduce CIP time, more operating time, higher production efficiency. Level control, absolute pressure, gauge pressure, temperatures, all are good data that help you monitor what's going on in your evaporator system that you can't necessarily see with your eyes. And of course, the turbofans come with a lot of instrumentation and data that do need to be monitored and maintained. And with automated controls, you have the capability of the control system to monitor all of that data that's coming in against known set points to give you alarms when you're trending out of specific ranges. Takes the load off the operators, allows you to trend and more exactly identify routine reoccurring problems by going back and looking at those trends. Always nice to have. And with that, I've been babbling on now here for 45 minutes. I do thank you all for your time. And hopefully you've been able to garnish something from this. There's a lot we can do in finding opportunities for energy efficiency in evaporators, and we're always willing to try.
Thanks, Bruce. We do have one question that's come in so far. How do you decide the size of the orifice?
That is by trial and error. And it is as simple as you try one, you monitor how the system is performing, try another larger or smaller, see how it's changed. And I mean, truly that is the only way to do it. We do try to do theoretical calculations to predict it ahead of time, but we always go to the field with a set and inevitably are switching them out, trying to find that optimum size.
Okay. Why don't we give folks an opportunity to type in some more questions if they want. Do you have the announcement for the next webinar coming up in your presentation, or do you need?
I do.
Perfect. Excellent. All right. So if anybody has any additional questions, you can use the Q&A feature to type them in. In the meantime, as you can see on our screen, our next webinar will be in 2 weeks on June 18th, troubleshooting spray dryer bag houses. And you can find details for that and all of our past webinars on the URL on your screen, caloris.com/caloris-webinars. If you want to be among the first to know about additional upcoming webinars, you can join our mailing list, and that's done by scrolling down to the bottom of any page on our website and entering your email address where prompted. We only send out 1 email a week. It's an industry e-newsletter with resources for plant managers and industry news, along with announcements like this. Bruce, there's another question that's come in. Can you use condensate removal per effect to determine when to clean the system?
And theoretically, yes. If you invest in either a volumetric device, which would be pretty easy to use with condensate, because the density is pretty constant. And if you chart that and monitor that you are getting reduced flow rate from an individual effect, that is a direct measure that you've got reduced condensation. And it might not necessarily be due to cleaning or fouling issues, but that's usually the first thing it's indicating.
Okay. If you have any additional questions, we do still have a couple minutes. And again, you can use that Q&A feature. If there are questions you have that you'd rather not ask in the webinar setting, you can always send either of us an email. The easiest way to do that is simply to email me at info@caloris.com. That goes directly to me, and then I will forward on your question to the appropriate person. We are also actively taking suggestions for webinar topics you'd like to see in the future. We do intend to offer this series throughout the summer. We'd love to hear about topics that you'd like to see. I don't see any other questions that have come in, so we thank everybody for joining us today. We hope that you enjoy the rest of your week and that we'll see you on a future webinar.
Thank you, Missy.
Thank you.